Okay, so what did we say a vector was? Something with magnitude and direction. A scalar?
Something with
Something with magnitude only. Give me an example of a scalar. Give me an example of a vector. Let's start with scalars. Give me what's kind of the classic example of a scalar? Mass. That's a really good one here. Classic example of a vector. Velocity, acceleration. Later on, we're going to find force. So next week, we're going to do the force table lab. And forces will be basically the vector we're going to break out. And I'll show you how those work. And how did we say we can actually denote a vector? Yeah, so what we do is that if you want to denote a vector, I'll call it V for no good reason, you put a half arrow over it like this. Now, if you look at a textbook, what might you see in a textbook? You may not see the half arrow, you might see
just a letter.
More about the letter. It's going to be bold. So it's going to be something like this. It's maybe similar to when you, if you're typing a paper for some English assignment and you click on some word and then you hit the bold option on Microsoft Word and it makes it bold. It's the same idea. Okay. We're not going to use this, frankly, because it's just a first class paper. So what you're going to do on your homework assignments, when you write them, you're going to use the half arrow. Now, if I want to draw a picture of these things, what do we do? What's the length of a vector specify? The magnitude. And the direction it's pointing is going to be then the direction. And how do we say vectors add? Graphically?
Yeah.
In a tip-to-tail fashion. So in the lab we do on Monday, we're going to do a lot of these pictures. I'm going to show you how to draw them. It's kind of neat. And then we're going to then do an experiment to see that our experiment agrees with our little picture. And then I want to show you how to break it up mathematically, which we're going to do today. Okay, so let's just take an example here. So let's say here's a vector here, A. Here's a vector here, B. And here's a vector here, C. Okay. And I want you to find D, and this is graphically, to be minus A, minus 2B, okay, plus C. Okay. How would you graphically do this? Meaning on the board. You're going to draw a pretty picture. Which vector do you have to start with? It doesn't matter. Again, I'm just kind of a left and right kind of guy, so I'm going to start with the left one, only because it's the first one. You don't have to. Okay. So what does minus A mean? Yeah, this would be normally A, but when you have the minus A, it means you flip the direction of it. So this would be, let's put it over here. That would be A. So minus A is going to be this fellow here. Now I'm going to add to that. Yeah, because this is really saying, you know, plus a minus A, plus a minus B, plus a minus B. That's what this is really what this is saying. Okay, so I'm going to add two negative vectors to this. So B itself would go this way. So minus B would be this one, and then this one here. Okay, I'll finish it up. C goes like this. So if I had C, I get this, that. So where's my vector D? It looks stupid, but it's correct.
Start at C.
I start at the tail of the first vector, and I go to the head of the last. So this is actually my vector here like this. What do you think the most common mistake is with these things?
You flip.
Yeah, well, okay, you flip it. Often it's going to be, let me be, because I wasn't very precise. What's the most common mistake with drawing D at the very end? Going from here to there. If I draw my arrow going this way, that's not quite D. That is instead, that's going to be minus D. Okay? And so you have to be careful with that as well. Okay? Questions to that? Okay, so now what I want to do is talk about something you know, and I'm going to kind of, it's going to seem like I'm beating the point to death, and I'm not. I just want to show you why this one thing works. I want to talk about a very useful concept behind vectors. So the vectors, Okay. We can think of vectors as being composed of other vectors called components. So any vector I have, I can think of that vector as being basically made up of other vectors. I'm going to call those components. If I add those two components together, I can get my vector V. Okay. So again, what I'm going to do is going to seem stupid, but there's a reason why I'm doing this, so just bear with me. So let's figure out how to do this. Here's my vector V. Okay. I go to one of my buddies and I say, hey, I want you to break that up into components. And one of my friends says, oh, this is easy. I can think of the first component of V as being this one, V1. And I'm going to add basically in a tip-to-tail fashion this vector here like that. Here's my V2. So here, my vector V is made up of this component and this component. Okay, now I go to my other friend. I tell my other friend, I need to break vector V into components. My other friend says, well, your friend over here is a jackass. They don't know what they're talking about because the real vectors are this one here. This is really V1. Okay. And this is really V2. These are the components. So I can think of this V here is this V1 and this V2, but my friend over here says, no, this vector here is really this V1 and this V2. So I go to my third friend. My third friend says, oh, morons. Well, my vector is really, here's my vector V. Your vector V1 comes out of the board like this, and vector V2 goes into the board like that. They're the true components of the vector. Okay, so what's the problem here? Again, what do you always want to do in science? Why is science useful? Because I can do something and convey it accurately to somebody else. They can then reproduce it and then take that information and go further with it. Okay, the problem is with this right here, if one friend does this, another friend does this, another friend does that. Okay, we can't communicate because we're all doing something different. So we need to put a restriction on here. So the restriction we're going to say on components is that components must be perpendicular to one another. So the components that make up a vector, they must be perpendicular. So we make a further stipulation. That components of a vector must be perpendicular to one another. Okay, so I go back to my first friend over here. My first friend says, got it. I know what to do. Okay. Here's my vector B. It says, okay, we need perpendicular components. Great. Well, here's my first component. And here's my second component. You see, they're mutually perpendicular. I do a tip-to-tail fashion and get B. Okay, I go to my second friend. My second friend says perpendicular, I got it. What you really need is this vector here. This is V1, and this component here, V2. And they're mutually perpendicular. Okay, now I go to my third friend, says perpendicular, I got it. It really comes out like this. This is V1, and then V2 is like that. Mutually perpendicular components. Okay, it's better. Okay, we're at least now we agree that they're perpendicular, but it's still everyone's disagreeing. So we need one further stipulation. So the further stipulation we're going to say is that those components, the perpendicular components, have to lie along the x-axis and have to lie along the y-axis. So to ensure that everyone has the same components, we insist that the components that make up the vector, the mutually perpendicular components make up the vector must be along the x, y, and z axis. Okay. We're not going to do a lot with the z-axis. I am going to show you how to do three-dimensional vectors in this course. But for the most part, in this course, we're only going to be doing two-dimensional vectors. But I do want you to do a little bit with three. They ain't hard, but just so you know, a lot of people have a hard time kind of visualizing these. Visualizing things in three dimensions is a useful skill. To be honest, it only comes with time. Okay, so let's try this. So now, what we do here, here's my vector B. I imagine now an XY axis. So here's my Y axis, and here's my X axis. Okay. And what you do to draw these, and again, a little bit soon, we're going to start taking XY axes that are oriented like this. They're going to be kind of twisted, and you're going to have to generalize this idea. This is what you do. Put your pen on the tip of the vector, and you drop the perpendicular to your x-axis here. I could go to the y-axis too. Either one is correct. So I go like this. That's perpendicular. Then this is this component here. I'll call this V1, which I'm just going to call Vx. I'm calling it Vx because that's my component along the x-axis. And here's my second vector here. If I edit in a tip-to-tail fashion, I'll call this one V2, or now I'm going to call it Vy. And these are my other components. So these right here, these are the components. So Vx and Vy are the components. The vector B. Does that make sense? Now we're going to do something which initially when you learn it seems really, really stupid. And it seems like all I'm doing is making it more complicated. And I'm not. Unfortunately, you're going to have to be in Calc 3 and more advanced courses to see how useful this is. But right now, when you first learn it, it looks like I'm just making the problem overly complicated. Okay, so we're going to introduce something more. Okay, so any questions with this? So from now on, if you're any form of engineer or physicist or mathematician, doesn't matter, okay? You will always use the components to be, they always have to be perpendicular, and they're always going to be taken along the x and y axis. Okay? If you go on to take more physics, I hope you all do, we'll generalize this idea to basically special relativity, and we'll have four-dimensional vectors. Then we have to figure out what happens with four-dimensional vectors. If you really want to have fun, then you take my course in general relativity, and I'll show you what happens when you go to curved space. Because it turns out things get a little funky in curved space. Okay, what is curved space? I'll just leave you with this. When you come in and when you come up when you stop at the traffic light, you come up the hill, there's the art museum on your left, and there's that beautiful white sculpture in front. And that is, I hope that sculpture is never removed. I hope it stays there forever, especially when I teach general relativity, because that's a perfect example of negative curvature. It's curved space. It has what's called negative curvature, and it's very hard to get negative curvature. And that sculpture is a perfect example of curved space, and curved space which has a negative curvature. Just whetting your appetite. You might think, no, I just destroyed your appetite. I did not. It's beautiful. Okay, so let's see what we can do here. We define three new vectors called unit vectors. Okay, any unit vector has a length of 1. Okay. And you denote a unit vector by putting a little caret, one of those little caret symbols or hat symbol. The unit vectors are denoted by this. You call this symbol hat. It's just like the caret symbol, but no one says caret. They all say hat. So we're going to have 3 vectors here. Our first unit vector is going to be I hat. The second unit vector is going to be called j hat. And our third unit vector is called k hat. I, j, and k. Okay. I hat here only points along the x-axis. J hat here only points along the y-axis. Okay. K hat here only points along the z-axis. Okay. Let's draw a picture and see what. Let's start off with just the next y-axis, then go to 3 dimensions. So here's my y-axis. And here's my x-axis. Okay. By definition, how does I hat have to go? I hat can only point along the x-axis here. So this right here is I hat. If I look at the magnitude of I hat, because it is a unit vector, okay, and what does unit mean in front of something? It means 1. So the length of any unit vector by definition is only 1. Okay. Now, how does j hat have to look? By definition, it can only go along the y-axis here. This is j hat, and again, the magnitude of j hat is by definition 1. Okay. Now, if I were to put a k hat in here, how would the k axis go? Or the z axis? How? It'd be like that. That'd be the z axis. And how would k hat have to go? Along that axis as well. Let me show you how to draw these. So, if you want to draw a three-dimensional axis, so to draw a 3D axis, okay, draw the z and y axes first. So this will be my z axis. This will be my y axis. Now, you have to make this 3D. Okay, so how do I make this look 3D if I want this axis coming out like this? Okay, you can't draw it 3D because it's not on board, so you have to do something kind of fake. So what you're going to do, you're going to have it you're going to have it come out like that. And that's your x-axis. And that represents an axis coming out like that. Okay, the chemist invariably will draw that arrow going that way, and it drives me nuts. I said it on an inorganic chemistry class once, and they always had the axis going in like that. It drove me nuts. Always do this. Okay. Now there's a subtle point here. I'm not going to hold you responsible for it, but it's going to become really important, especially if you do more advanced stuff in engineering and physics and math. Only draw this axis here or a proper or a proper rotation of it. And this is what I mean. I'm going to do it with my fingers. Okay, so if this is my z-axis, this is my x-axis, and this is my y-axis. I can do this axis, 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 I can do that axis, I can do this axis. Any of those axes are fine. Do not do the following. Do not have Y, X, and Z. In other words, don't flip these two. Okay? If you do, that's called a left-handed coordinate system. So this axis right here, this is called right-handed. And any proper rotation of it is right. If you flip any two of these, you get what's called a left-handed coordinate system. And fundamental things are going to get screwed up for you. You don't know that yet. Okay, but that ends up getting screwed up. It's a fine point. What do you think happens with a left-handed coordinate system? I'll give you just a little more advanced information. A left-handed coordinate system is basically the mirror image of something. And let me show you how that works. So here's my z-axis, here's my x-axis, and here's my y-axis. This is a right-handed coordinate system. Imagine I have a mirror here. This is a mirror. Okay. So in the mirror, if I'm looking at the image of my mirror, if this is my z-axis, how would my image look over here? It look the same, right? Z-axis, z-axis. How would my x-axis look in a mirror?
Same.
Same. Okay. Now, how would my y-axis look?
It'd be awesome.
It's this. Okay. There's no way I can take this, if this is x and if this is y, there's no way I can rotate this hand to give me this hand here. That's a mirror image. You could say, well, who on earth cares? Okay, it turns out we're gonna get something called a cross product pretty soon. It's a way of multiplying vectors, and they're all based on a right-handed coordinate system. Okay, and if you want a more abstract reason of this, is the following. Don't even worry about this, but I'm going to tell you what it is. Okay, for the longest time, people thought that how would physics differ if you're in a mirror? In other words, if you were Atlas and if you went into the looking glass, what would happen to your physics there? And everyone said it would have to be the same. Perfectly acceptable thing. Well, you can actually do an experiment on this. And the famous experiment was done by Madame Wu. She actually had a very, very clever way of actually checking physics in a mirror. Remarkably clever. Okay, and it turns out it's different. It turns out that physics in a mirror is different from physics outside the mirror. So Alice would have different physics. Okay, and so that's a more subtle point. Take my course in particle physics, and I'll show you in extreme detail what goes on with that. Okay. So this is our coordinate system here. Now let's draw these. So how would my x-axis, how would my I-hat look? This is going to be I-hat. Okay. J-hat, this way. And then K-hat, up. So if I had to use markers for this, it'd be this. This would be K-hat. That would be I-hat. This would be J-hat. There. That's what this would look like. Okay, that makes sense. What we'll do, I'll show you what happens if you have a vector coming out like that. How do you break them into X, Y, and Z components? I'll show you how to do that, but not today. Okay, so let's go on to this. So you could say, well, well, thank you for the completely useless information. Okay, it turns out it's not as useful. Let's do an example here. Let's ask what is, or I'll say draw. Draw the vector. A equals 3 I-hat plus 2, let's say plus 5 J-hat. Okay. You tell me how to draw that now. I'll give you a hint. You're pro at this. What does 3 I-hat mean? That is I-hat plus I-hat plus I-hat. Oh, it is 5 J-hat. Well, maybe I should use a smaller number. Okay, there's going to be 5 of the J's put together, right? Plus J-hat plus J-hat plus J-hat plus J-hat plus J-hat. So if you were to draw this thing, what would you do? Here's your XY axis. So I'd have I-hat plus I-hat plus I-hat. I'm going to have, you don't have to erase this. I just have to lower it because I'm going to run out of room. I-hat, I-hat, I-hat. Okay. So this right here is my This is my 3I hat. Now, what is j hat? Again, vectors add in the tip to tail fashion. All I'm doing is a tip to tail fashion here. J hat, j hat, j hat, j hat, j hat. Do I have 5 of these? Yes, I do. So my vector A is that. Does that make sense? So really all this is here. This is nothing but my AX component. And this is nothing but my AY component. Okay. That makes sense? What would be the magnitude of my vector A? In other words, I want the length of this guy here. You do the Pythagorean theorem. Okay. So what do you do here? You take this length here, 3. So I would take the magnitude of x hat, okay, square it, plus the magnitude of y hat, square that, and take the square root. Okay. So this is what? This would be 3 squared plus 5 squared here, square root of that. Okay, let's pause a minute. Okay. Very frequently, what do you think I get for that? And it always makes me cry. Okay, let me give you a hint of because you can't, obviously, you don't know what I'm thinking. What do I not want to see you write that as? And it just makes me cry. If you want me to just kind of reach into my heart and just kind of grab my chest because I feel like my heart's going to stop. Okay, what will you write that as? You say, oh, this is easy. This is nothing but the square root of 3 squared plus the square root of 5 squared. Hey, well, this is 3. This is 5. This is 8. So simple. Okay, I will see that. Okay, every time I can feel my little heart just tightening up on me. Okay, okay, you can never do this, right? If you have the square root of a squared plus b squared, this under no circumstances equals the square root of a squared plus the square root of b squared equals ab. That never ever happens. Okay. So what would you have here? You have square root of 9 plus 25. This would be the square root of 2. That'd be your magnitude. The other one, and this is more subtle here, don't ever write the following. Don't do this. Don't say, oh, this is easy. I'm going to take my 3i squared. I'm going to add it to my 5j squared and square root that. Okay, do not write it like this. Anyone know why that one's a little more subtle? Okay, what does this say? This says 3i hat times 3i hat. Okay, it turns out that I hat times I hat is an actual animal that lives in the physics zoo. Okay, it's referred to as a didactic product, and it's actually a beast straight from hell. That if you're walking through the jungles one day and you happen to see an I times I coming at you, run like hell, because that's a nasty beast. That's a really hard animal to deal with. Okay, you'd panic. Hey, how would you panic? Word. Okay, more. What are the 3 things you're panicking? Go in a circle, hands up. Okay, you do that, and then you can panic properly. That's what would happen if you saw an I hat times I hat. Okay, so it would be a really nasty beast. Okay. Okay, well, that's nice. Hey, how would I find this angle here? You could. Which one of those would I use? Probably. You can do a lot of different ones.
What'd you do, like cosine?
Cosine would work fine.
Like y over x?
Yeah, you could cosine be fine. Another one would be somebody said sine, and then also then the tangent. Okay, I'm going to do it with the tangent just because this is the one that you normally see with this. So, what is the tangent again? Tangent is opposite over adjacent. Okay, so this is your opposite over adjacent. So in this case here, if you look at your triangle here, what is your opposite side here?
5.
It's just 5, because we're just dealing with the length. So the length is 5. Your adjacent side is, give me this length here, that'll be 3. Okay, so your theta is going to be your inverse tangent of 5 over 3. There's another thing I always teach my students, it's very important. Theta has another very important property. What does it become? Mr. Peanut. You can put a little hat on him. Eyes, put a little monocle here like this. Becomes Mr. Peanut. It's a very subtle property of theta. Suppose you have Mr. Peanut from space. You're reviewing all the important things in this class. Okay? How do you know if you're ever dealing with a space alien? Okay, antenna.
Ears. Yeah.
What about the ears? Oh, they're pointed. Okay. How many eyes? 1.
And that one has
So that would be Mr. Peanut from space. Suppose it's an evil Mr. Peanut from space. Pointed teeth. Okay. Very subtle problem. A lot of people don't teach you this in general physics. You know, the fools. You know, I want you to be safe when you're walking in the woods. Okay? And if you come across Mr. Evil Peanut, Mr. Evil Space Peanut might have eye times eye with it. Oh, then you really are in trouble. It's good to know. Questions of this? Not all this crap here. I'm talking about Mr. Peanut. Okay, let's try another one. Let's say I have this. Let's say I have vector B. This is minus 2 I hat plus 3 j hat. What is that? If I say draw it now. Okay. Okay. So this minus sign goes with the I hat. I hat, remember, is the vector that always goes this way. That's your unit vector. But if I have a minus vector, what does it do? It flips. So what is this? This is really I hat minus I hat minus I hat. So this right here, this is my x component. What am I adding to this in a tip to tail fashion? The 3 j hats. J hat, j hat, j hat. All right. So this right here is my vector B. And this right, should be B. This right here would be my by. Okay. Now, what would be then the magnitude of B?
magnitude of units.
So I'm going to have the magnitude of bx squared here, which is going to be what? Okay, I would take the magnitude, I would take the length of this guy here, which is minus 2 and I square it. Now, why am I going to run into trouble here? Well, let's go, just keep on going. Plus, I take this side here, then I add it to
I squared.
this length here squared. I'm just doing Pythagorean theorem. Now tell me why that's not going to work for me here. You have to be really careful here.
Negatives, not parentheses.
Exactly. If you leave it like this is minus 4 plus 9, and that's not going to work. When you do these things, all the terms in there are always positive. So really what you have is you have this. Does that make sense? Okay. And again, I'll see those things here. Okay, so what this would then be 4 plus 9 square root thereof square root. Okay. Now suppose I want an angle here. Okay, now I'm going to tell you how angles are always specified. But then I'm also going to show you what I'm going to do with an angle. Okay, so in mathematics, how do you always specify an angle? Always. Sure, but from where to where? You always start at the x-axis and you go clockwise or counterclockwise. You always go counterclockwise like this. This is how you specify an angle. So in this case here, this right here is theta. Okay. It always starts at the x-axis and you go counterclockwise or whatever. That's how you always specify an angle. Okay. Now, I don't like angles like that frequently. So what I'm going to do is I'm going to say, yeah, okay, I like my angles always to be less than 90 degrees because I'm not very smart and I need an angle to be less than 90 degrees. So I'm going to call this my angle here theta. Why? Just because it's easier to me to work with. Now, if I'm calling this my angle theta here, how am I going to then calculate this? Tell me how to find it. Tell me how to find this angle. Yeah, it's going to be tangent of theta again. It's opposite over adjacent. The opposite will be 3. The adjacent will be using my angle here.
2.
Going to be 2. Do not put in, okay, you can, but I do not put in -2 because I don't want this angle here. Okay, I want this angle here. Just because I want an angle less than 90 degrees. Okay, so I'm going to have this here, then I take my little inverse tangent of it. What's another name for inverse tangent, or inverse sine, or inverse cosine?
Arctan.
Arctan, arcsine, arccosine. You have this. That makes sense? How could I then calculate this angle here? I could, but I'm lazy. I have this number. What can I do? I can take this angle here, which I know is 180. I can subtract that and then give me this. That makes sense? Now, you could say, well, this is all fine and good, but I'm not seeing this is really helping. Okay, so often what you do is you're given vectors in terms of this I, J, and K notation. So let's ask why. The reason why is okay. Suppose, so here's your answer. Suppose we wish to add 3 vectors. Oh, let's say 2 vectors. Okay, so let's say I'm going to call this, I'm going to say, here's my A here. I'm going to have a number like this. 5i hat plus 2j hat. Another vector here, which is going to be minus 3i hat plus 4j hat. I want to find C equals A plus B. Now I could draw these out and I could do a tip to tail fashion, and that's completely correct. But what's the problem with drawing these out? It's not wrong. Just from a practical point of view. Okay, there's going to be a lot of effort, but there's something else. And you're going to find out this, we're going to do this in lab. We're going to add these by hand. And you're going to see that it's going to be easy, but by a lot of effort, what do you mean? You have to be really careful. You're going to have to really, it's going to turn out that when you actually do this in principle, kind of a tip to tail fashion, it's going to be really kind of hard. You're going to see that in lab. It's not conceptually hard, but it's going to be hard in the sense that you have to be really careful and measure things well and whatnot. So this way here, though, you can turn off your brain. You can say, oh, see, this is my friend A. I know what A is. Hey, I know what B is. Hey, now we just add things. How many I hats do I have? I have 5 over here, but I also have minus 3 over here. So what is this? This is going to be nothing but 2 I hats. Hey, how many J hats do I have? Yeah, I have 2 over here, but I have another 2 over here. I add like terms again. And this just gives me then 6j. Done. Boom. Okay. That makes sense? If I had this, I had the vector d equals 2a hat minus 3b hat. What would that have to? Well, the beauty of this is you just turn off your brain and you do it. You just substitute this in. You have 2. What is my friend A? My friend A is here. It's this 5i hat plus 2j hat. And I have my friend here minus 3. B is my buddy over here. Yeah. I multiply everything throughout here. So this gives me 10i hat plus 4j hat. This times this, so this gives me plus 9i hat minus 12j hat. Hey, how many I hats do I have? 19. Okay, and j hats? Minus 8. Boom. Okay, that makes sense. All right, just so you know, those of you who are engineers, often you don't use I, j, and k. You use x hat, y hat, and j hat. That's not what I learned. That's not usually what's done in physics. It's not usually what's done in math. Usually what's always is I, j, k. But just so you know, for the engineers, you might have an x hat here, you might have a y hat here, you might have a z hat. But it's the exact same amount. It's the same reasoning. There's no changing. It doesn't change at all. Does that make sense? Now let me just do one more thing with this. So when you have chalk just continues to chalk until there's no more chalk, and the little piece of chalk goes to chalk heaven. These just go to marker heaven kind of. Now these are refillable. So they start going up to marker heaven, and then we can bring them back down in the refilling process. We're learning theology in this class too. Amazing. We're learning theology. We learned about Mr. Peanut, what to do if you're chased by II. Is there no end to what we're learning in this class? Imagine what would happen if we're actually learning physics. Imagine how much we would actually be learning. I'm trying to teach my class with 10% more truth than the last time I taught it. So this class would be 10% more truthier than the last time. We'll learn so much that you might even be able to fill up 1 3x5 card with it. That's how much knowledge we're going to learn in this class. Enough to fill up 1 3x5. Wow, imagine what would happen if we were actually learning physics the entire semester. Great. Okay, so what do we have here? What are we doing? We're doing the following. So a generic vector A and generic vector B can be written as, and so I can write A. What's the most general way I can then write a vector A now? I could say how long I want to go in the I direction. So I could say I want to go some distance IX in the I direction. So this AX is nothing but a number. This is just a number. Okay. And then how much do I want to go in the Y direction? So AY J hat. So these are just numbers. Then I can do the exact same thing then for B. And say that this is BX I hat plus BY J hat. Again, these are just numbers. So I can have here, if I then said C equals A plus B, what does that give me? This gives me AX I hat. Let's say YJ hat. This is my vector A. Then I add my vector B, my buddy here. Okay. Well, tell me what I have in the I direction. How far am I going in the I direction?
A.
Say it right. You're thinking right just now, say it mathematically correctly. If I add these two together, right? What do I get? AX
Plus views.
plus BX. You need the plus. No, corresponding for the Y, you have
A1.
AY plus BY. Okay, well, generically, how do you think I can write any vector C? The most general way to write a vector C is C, just in terms of C stuff.
Gotcha.
C vector I could write as CX,
Plus
CX, I hat plus
C.
CY, J hat. Okay, let's compare the two sides. If this is I hat here with some number in front of it, and if this is I hat here with some number in front of it, hey, these two numbers must be the same. So this tells me that CX equals AX plus BX. Okay. Well, hey, what else happens here? If here's I hat, if here's I hat, this is the vector with the number in front of it. This is the vector with the number in front of it. Hey, it must mean that this term here is equal to this term here. So this tells me that CY equals AY plus BY. So what does this tell you? This tells you that when you add vectors together, what happens? All the X components add together. Now the Y components add together. Okay, and we're going to do that in the lab too. So when you do the lab, you have vectors, and we're going to add them three ways. One is that we're going to add their components together like this. We're getting some vectors. And then what else are we going to do? We're going to then do a tip-to-tail picture. We're going to get those. And we're going to see that this and the tip-to-tail picture work. And then we're going to have a little table. We're going to set the vectors up on tables and measure it. We're going to see that they work. So we're going to see that the measurement corresponds to this, corresponds to our diagram. And we're going to do that for like 5 or 6 setups. Okay, I'll do one of them for you. One of them we're going to do as Simon says, we're going to do together. And then I turn you over to the rest of your partners, and then you're going to work out your other cases by yourself. Okay, this kind of is a very, very nice slide. Questions for that? How am I doing on time? 2 minutes. Okay, questions with this? Let me give you just one more thing. Okay, what did we say a unit vector in general is? A unit vector is any vector that has a length of 1. So let's ask, how can you write the unit vector for a generic vector? Okay, so here's a vector A vector. And I wanted the unit vector A. I want to find A hat. So this would be the unit vector of A. Okay. So the unit vector of A is going to be what? It's going to be a vector that points along the direction of A, but it's going to have a length of 1. So the A unit vector, if I had to draw it in here, would be this. That would be the A unit vector. It points along the direction of A, but it has a length of 1. So A points along A, but has a length of 1, meaning the magnitude of A by definition is 1. With that said, I've finished my time. Think about that, and I'll give you the answer on Monday. Okay? Have a great weekend.